Okay, guys, so what we're going to be doing is we are now going to take a step back from looking at the chain rule like we were, because I know a lot of people didn't care for that too much. And instead, what we're going to do is we're going to start looking at how to use the derivative in a variety of different ways. One of the ways that we're going to look at that is how we can describe what's going on with a graph without looking at a graphing calculator. And so that's what we're going to be doing by using the derivative over this next unit. Okay, so just kind of keep that in mind. We call it graphical analysis, or curve sketching is what it's called sometimes as well. So when we look at a graph like this one, I'm hoping most of us, if we look at a graph, we realize that when we describe what is happening with a graph, first of all, we always are moving from left to right. So in this case, if I was describing what's happening with this graph, I always move from left to right. And if I was talking about where the function's increasing, that just means we're looking at different intervals where the y values are getting bigger. So all of these places that I am circling currently, that would be all of the different places that my function is increasing. And we use x values to describe that. Where the function is decreasing is the exact, we look at it the same way, moving from left to right, but it's decreasing anywhere the y values are getting smaller as we move from left to right. Okay, so we can see, I've drawn it slightly differently there, but we can see where the function is decreasing by looking at that. And then if I wanted to know where the maxima and minima occur, that's just maximums and minimums, and notice it does say relative maximums or minimums. That's kind of each of these turning points where we change from increasing to decreasing. So in this case, I would have 4 maximums or minimas. These two down here are mins because we changed from decreasing to increasing, and these would be maxes right here. Okay, so if I have a picture of a graph, I would describe all of those things using x values, but it'd be pretty easy to do looking at the graph, even though the function here, so I have a fairly difficult function that I'm looking at. That function might be kind of hard to actually analyze what is going on. Now, one thing that is true about a function, whenever it is increasing, and this is just true in general, is anytime it's increasing, we can say that the derivative of that function, when we took the derivative and plugged in a value on that interval. So if I'm looking at a function like this, and I can see that my function's increasing right here, if I take any x value that is on that interval and put it into the derivative, I would see that the slope of the tangent line, it's a really bad tangent line that I've drawn there, still bad, but I would see that the slope of the tangent line, I wouldn't know what it is every single time, but I would know that it would always be positive. And so when it's decreasing, the exact same thing, exact same analysis would be true if I had a function that looked like this. If I looked at where the function was decreasing and I drew a tangent line right there, or anywhere that the function was decreasing, I would see that if I took my derivative and plugged in that x value, I would always get a negative slope. So I'd have a negative derivative value. And then at a local max or min, hopefully you can see that if I were to draw the derivative, or excuse me, if I were to draw a tangent line and use the derivative to find the slope of the tangent line at those points, then my slope every single time would be 0. Now, a local maximum is just a point that is slightly above or slightly below the points around it. So I can have multiple maxes or mins on one graph, and there's nothing wrong with that if they're local maximums. So there's a local max there, a local max there. Then we have a local min in that graph that I just drew. Okay? So what we're going to do, hopefully you can see, because we're talking an awful lot about tangent lines, is we are going to use the derivative to help us understand what is going on. So in this case, if I had my function x squared plus 4x minus 1, now hopefully you know that my function is going to look something like that. And I chose this function on purpose so that we could see that even though we know what a function looks like, we can describe its behavior by using the derivative. Okay? So the derivative in this case would be 2x plus 4. Now, the derivative, again, what it would tell us is what we just talked about before. If I were to take a number and plug it into the derivative, if I get a positive number, then that tells me at that point my function's increasing. If I were to take a number and plug it into the derivative and I get a negative number, that would tell me at that x value my function is decreasing. And if I were to plug an x value in and I were to get 0, then I might have one of those maxes or the relative maxes or mins that we were talking about before. Okay? The key here is understanding that the zeros are by far the most important part of this analysis that we're about to do. All of these places that I draw a slope of 0 on these points, notice that even though there's quite a few of them here, I only have 4 different places where if I draw a tangent line, it has a slope of 0. Notice if I were to talk about where the function's increasing, there are a ton of points, ton of x values where my function's increasing. Like there's a lot. And there's a ton of points where my function is decreasing. So what we're going to do, the idea here is we're saying, okay, I'm going to find out where the derivative is equal to 0 because that doesn't happen very many points on the graph. And then I'm going to kind of work backwards from that. Now, when we go and find out where the derivative is equal to 0, or where the tangent line has a slope of 0, we have what is called a critical point. So all of these places that we drew these tangent lines with a slope of 0, those x values, we have what is called a critical point. Okay? That, again, is where the first derivative is 0. And the reason for that is because there are just a few of those at most on a graph, what we're going to do is we're going to work backwards, because before that point, and here's the idea behind a critical point, that is the only place on a graph where we can change from increasing to decreasing, or vice versa. Those are the only places, and so it makes sense to say, okay, these are the only places where I can change direction, if you will, so I should work backwards from those points in order to tell what is happening on the original function. Because there's a million x values where it's increasing, there's a million x values where it's decreasing. But at most, we'll have like 4 points where the slope of the tangent line is equal to 0, and we have these critical points where it would change direction. Okay? So here's what we're going to do, and this is kind of what this is saying. Let me just get to an example because it actually makes more sense skipping those. Okay, so let's say I had this function, y equals x squared plus 4x plus 1, same one we were looking at before. And I want to know where this function is increasing and decreasing. So what I would do is this. We already know the derivative is 2x plus 4. I would go and I would find my critical point. Now my critical point, again, is just where the slope of the tangent line is equal to 0. So we would take our derivative and set it equal to 0 with the intent of finding the x value that this is going to happen at. So I get 2x equals negative 4, so x equals negative 2. What that's saying is x equals negative 2 is our critical point. That is the only place on this entire function that our derivative will equal 0, and we will have either one of those maxes or mins. Now, again, we know what this graph looks like, but let's say we didn't. What we would do next is we would take that number that we just found and we would put that number, or if there's more than one of them, those numbers on a number line. So I take negative 2 and I put it on a number line. Then what we do is we take any number that is smaller than negative 2, because less than negative 2, the graph has to behave one way. It's either increasing or it's decreasing, but it can't change because we don't have any critical points that are smaller than negative 2. So I take a number smaller than negative 2. Let's go with like negative 5. And it can be any number. There's no specific number you have to choose. And we take that number, and what we do is we take it and plug that in to the derivative. Now, honestly, that will tell us what the slope is. I don't care what the number is. I just care whether it's positive or negative. Because if I get a negative number, that means that the function or the tangent line has a negative slope, which means the function must be decreasing at that point. If I get a positive number, then that means that the function is going to be increasing. So in this case, 2 times negative 5 plus 4 gives me a negative number, which means my function is decreasing at that point, and what that tells us is it's decreasing at all of the other points that are less than negative 2. All the way up to negative 2, this function now we know has to be decreasing. If I choose a number bigger than 2, and if you can choose 0 at any time, you should always choose it because it's by far the easiest to evaluate. I take 0, I plug it in, 2 times 0 is 0, plus 4 gives me a positive number. Now again, this matches up with what we were talking about before because we knew this was shaped like a parabola. So if that number is positive, then all of the numbers over that are bigger than negative 2 will give me a positive slope for my tangent line, which means they will always be increasing no matter what once we get past -2. So if I were to ask you where is this function increasing, you would say all the way from -2 to infinity. If I were to ask you where this function is decreasing, you could say from -infinity all the way to -2. And if you think about it, because the function changes from decreasing to increasing, so since we changed from a negative derivative value to a positive derivative value, at x equals -2, we have at least a local minimum, okay? So hopefully that kind of makes sense, and that's what we're talking about here. And that's all of those steps, that's what we were talking about. So in general, if we needed to have some steps to follow, here's the steps we would take. And I'm going to talk about them quickly, and then if you need to, you can pause this and just copy these down. Step number 1, we take the derivative, set it equal to 0 to find our critical points. Step number 2, we put those points on a number line, and then we choose x values that are either smaller or larger than those to tell what the function is doing before we get to that critical point. Step number 3 is to just make an interpretation like we did. Once we get to that point, we can say, you know what? I know what this function is doing based on the fact that I used the derivative to figure that out. So there's those 3 steps. Again, if you need to pause it, go ahead and do that, but we're going to move on and continue on with this next example. So if I had this function and I wanted to know everything about it, the first thing I would ask myself is, where are the critical points? Well, in order to do that, I have to take my derivative, which in this case would be x squared minus 4x minus 5, and then I would take that and set it equal to 0. Now you'll notice this function's a bit more complicated, so maybe we don't know what it looks like. What we have to do here is, in order to solve this equation, we have to factor. So I get x minus 5, x plus 1, and that gives me x equals 5 and -1 as my critical points. So what I do now, step number 2, has us putting these numbers on a number line. Now, we do have to put them in order from least to greatest, so -1 comes first, 5 comes second. Then what we do is we just start choosing numbers to plug into the derivative to tell what is happening at those x values. So a number that is smaller than 1 is like -4 we'll go with. Now, what we're going to do with -4 is we are going to plug that in to our derivative. The best part, and you can plug it in anywhere you want, and that's fine, but remember, we only care whether it's positive or negative. So in this case, to me, it makes the most sense to take -4 and plug it into my factored form. Because if I've got -4 minus 5, I know that that's a negative number. And then -4 plus 1 also gives me a negative number. So a negative number times a negative number gives me a positive number. And hopefully that makes sense what we did right there. I only care whether it's positive or negative, not what the number actually is. Now what that tells me is all the way from -infinity all the way to -1, I now know my function is increasing. If I were to choose a number between -1 and 5, something like 0, I take that and I plug it in. -0 minus 5 gives me a negative number. 0 plus 1 gives me a positive number. A negative times a positive gives me a negative number, which means between -1 and +5, I now know my function is decreasing. And if I choose a number bigger than 5, let's go with like 24601. I take that, I plug that in, and I get 2 positive numbers, which means my function is increasing again. So if I wanted to know where my function's increasing, I would say all the way from -infinity to -1 and from 5 to +infinity. Where it's decreasing is from -1 to 5. And we could say at x equals -1, because the function goes from increasing to decreasing, we have a relative max there. And at x equals -5, because the function goes from decreasing to increasing, we have a relative min there. Now, hopefully all of that kind of makes sense, what we did there, what was going on, everything that kind of applies to this. We can now notice I didn't draw the function at all. I didn't use my calculator, and we know exactly where the function's increasing, where it's decreasing, where we have relative maxes, and where we have relative mins. And what we're going to do in the future is kind of build off of this idea to tell even more about what's happening on the graph and how we can tell better what's going on. But for now, that's where we're going to stop with our graphical analysis or curve sketching. And hopefully you've understood that. If you have any questions, please come on in, and I'm more than willing to answer any questions that you have.